So because like each vertex is entering the queue once, and for each vertex we are checking for n minus one
Let
edges.
me go back to yesterday's this thing. Give me 1 second. You are saying when we run this inside a loop, uh, when we run the BFS inside a loop, that's what you're saying, huh?
Yeah, for the whole graph.
For the entire thing, correct?
Yeah.
So each time you run it, it will nevertheless take order n squared time from every vertex. Is that not correct? Am I making a mistake here?
So like I did not think like that. I was thinking like for the whole graph, each vertex will enter the queue once and to leave the queue once, and then for each vertex we'll be checking for n minus one edges. So each edge will be checked twice. So the order.
Maybe you are correct. Maybe you are correct. So that will be order n squared and not order n cube.
Yeah.
That's true. Because while there are three loops, it will not just not enter the queue multiple times. Correct?
Yes.
Okay. So good. Okay. Thanks for the clarification.
Okay.
So, uh, so what is breadth first search? We just saw that it was level by level exploration of the graph.
Sir,
Tell me.
just a thing. Could you upload the notes and the recordings of the classes till now since the 11th lecture?
The recordings are there. All the recordings should be there by now.
Okay. So actually, from the 11th lecture, I don't think it's there, and the notes in general as well.
Notes I will certainly put up today. Okay, I will do that. But just double check and check. You are Soham, no?
Yes, sir. I think Soham could not upload last class, so that's it.
Okay, or no. So he wrote to me saying that I need to upload the lectures, which I've done just like half an hour ago.
All right, sir. Thank you.
So just double check, and if there is a problem, then let me know. Okay.
Sure.
Okay. So we have level by level exploration of the graph. We can compute distances. And we can compute a spanning tree, a minimum distance tree. Shortest path tree. Here, shortest path. In terms of number of the weights of the edges, we don't consider weights. That you will see in the algorithms course, something called Dijkstra. But right now we are not going to talk about that. Then you can also use it to detect cycles. Every non-tree edge indicates a cycle. Correct? So this is what we saw about BFS. Now we are going to see another paradigm for exploring graphs, which is called DFS or depth first search. Correct? So in BFS, what you did was you looked at the vertices level by level. It was breadth first. You look at things at one level, then at the next level, then at the next level. In DFS, you go to one vertex, and while there are unexplored things adjacent to it, you go to that vertex and you go deeper and deeper and deeper till you cannot go further. Then you backtrack, and then you go forward again. And this alternating backtracking and going forward in a systematic way is called depth first search. Correct? So you search for neighbors, and backtrack if no unmarked, unexplored neighbor found, correct? You backtrack if no, when you cannot go forward. Way of going forward, correct? We'll make this precise in a second. So what is the DFS explore for V, for a vertex V? So we'll write this routine DFS explore V, and what it does is it marks the vertex as usual, correct? And then for each edge V comma W, that is for each neighbor W of V, what do? You just check if mark W is it's unmarked. If the neighbor is unmarked, then DFS explore W, correct? So tell me. So you are going depth first in the graph. Yeah.
So shouldn't we also mark the vertex V over here?
The vertex V?
I mean, after if mark is equal to W, like
that
so
will be
that
done inside this DFS explore W, correct? So you will call this DFS explore W, which will come here and mark W equal to 1. And then for each edge W comma W prime, if mark W prime equal to 0, then DFS explore W prime, and that will again come here and so on, correct?
yes, yes.
So this is the first step in the DFS explore. We assume that V has not been explored, correct? Okay, so that's checked outside the place where this DFS explorer is called, and now so let's run this on a small example like yesterday's example and see what happens. So let's run it on this. I don't know whether we gave the same numbers or not. Let's just some arbitrary, correct? So what would you do? So first you would mark, you suppose you start from 1, correct? So you call DFS explore 1, DFS explore, first you call with 1, correct? Everything is unmarked initially, so I should say that initialize mark equal 0 for all p, correct? That initialization is done. So first you would DFS explore V, that would in turn call DFS explore, and let me create the mark this thing also 1 2 3 4 5 7 8. So the mark is initially all zeros. I will not write that. So you mark 1, you mark this by putting a 1 here. Then you would call DFS explore its neighbors. So DFS explore 2, correct? Let's say. So then you would go here and mark 2, and in DFS Explorer 2, you would call its one neighbor is 1, so you might call with 1, and but you will not call DFS Explorer with 1 because you will see that mark 1 equal to z is equal to 1 already. So this will stop you from calling DFS Explorer 1. Are you with me?
Yes.
Then you would call DFS Explorer with 4, correct? And you would inside that you would mark 4. Then you would call it DFS Explorer with 3. So 2 it will not be called because 2 is already marked. Then you would call it with 3. So 3 is marked, and so on. So 1, 2, 4, 3, and then you would visit 5. Then you would visit 1 or 6 or 7. So let's say 7, and then 8, and then 6. So is the procedure clear? In this,
Sir, it's so should we write like for one of the edges VW
sorry, for one of the,
in the loop? Shouldn't we write for one of the edge VW? Like if we are writing for each edge, then
so for each edge, you will do it in sequence. You will first do the first edge, then the second edge, and so on. While there are more edges, you do this one by one, correct?
okay,
So,
sir.
So this might not have been a great example because this seems to give a, one second, sorry. Did you lose my screen?
Yes, sir.
Yeah. So yeah, so this seems to indicate that you would only go in one linear path, which is also called a Hamiltonian path. That's not necessarily true because let me add another vertex here. Let's call it 9. So in the modified thing, you would come to 4, and maybe you would go to 3 and complete this. Then you would backtrack. So you look for other neighbors of 6, there are no other neighbors. 8, are there other neighbors? No. 7, 5, 3, 4. 4 has another neighbor. So there is a branching here. Correct? So after 6, we would backtrack and come all the way to 4, and then there is 9. Correct? Are you with me?
Yes, sir.
Okay. So having said that, now this DFS Explorer procedure, you can also make it count the number of, to mark the number of components. And how would you do that? You would just DFS Explorer, and you add argument C, and you say mark V comma mark V equal to C, and if mark V equal to 0, dx equal to V comma C. So then mark everything with this C. How would you use it globally? So you would do def DFS G, which is now you do the initialization and everything. So for each V in G, mark v equal to 0, and you also initialize component equal to 0, which means that you are in the 0th component currently. There's no component you've seen. And now you write a type true. For each v in B or in G, whatever, for each v, for each v, if mark v equal to 0, then now you have means that you are now at a component, a new component. So you increment your component plus 1 plus equal to 1, and you then call DFS explore v comma component. So everything in the same component will be marked with this value component, correct? Which is initially 1 after the first unmarked vertex is discovered. And then you go to another component and so on, correct? So is the procedure clear? These two things?
Yes, sir.
Okay, very good. So now in this case, what are the non-tree edges? So we can similarly, like in BFS, we can mark a tree also, correct? How would you mark a tree? Well, in whenever you discover this VW and you are marking W from here, then you say, so parent of V is equal to, a parent of W is equal to V, correct? And initialize parent of V to be equal to -1. Does this make sense? So
Yes.
When put a parent pointer like this, similarly a parent pointer like this, a parent pointer like this, and like this, like this. So these blue things are parent pointers, and then you go back and you put the parent pointer. Okay. So now, what are the non-tree edges? What are the non-tree edges? Can we mark the non-tree edges? Let's say this is a non-tree edge. This is a non-tree edge, and that's it. These two are the non-tree edges, correct? Do you agree?
Yeah.
So now, what can we say about these non-tree edges? Remember, in the BFS, all non-tree edges were cross edges. BFS, non-tree edges. These were cross edges, meaning their parents were not ancestor or children of or descendant of each other. But here, all edges are reverse edges, back edges. By that I mean, look at this edge 3, 1. 1 is an ancestor of 3 in the tree. By following, you can reach from 3 to 1. Similarly, you can reach from 6 to 5 by following. So these are backyard ancestor descendants of each other, correct? The back edges are, and there are no cross edges. Why are there no cross edges? Suppose there were a cross edge like, so why can't there be an edge like this? Here 6 and 9 are not ancestor descendant of each other, correct? They are on different branches. So why can't there be an edge between them? Anybody?
Sir, if we had gone from 9 to 6, for example, then the other edges can't have been there because 6 would have already been marked. And similarly,
So first we would reach 6, correct? In this tree, we reach 6 first. Then you are saying while 6 has a neighbor like 9, which is unexplored, we would have taken this edge, correct?
Yes, sir. Yeah.
So there would have been, so then it would have been a tree edge rather than a back edge. Notice this is only for undirected graphs. Where you can go both from 6 to 9 and from 9 to 6, correct? Correct? So there are no cross edges in DFS, and there are no back edges in BFS. Okay, I'll let you convince yourself that this is correct. But the basic idea is obvious that in DFS you cannot, you will first visit all the neighbors and then only you would proceed to, then you would backtrack from that node. So it cannot be that there is a cross edge because the cross edge would become a tree edge. Correct? So without belaboring the point too much, let me move on. So any questions till now? No questions. Okay, good. So now, so far we have drawn this tree and so on. We would like to see even more structure in this graph. So let's define two auxiliary procedures. Let me copy this DFS Explorer again and modify it. So let me introduce pre-visit V and write post-visit. And let me define these pre-visit and post-visit. So pre-visit just does the following. It has a global counter. So time is equal to plus equal to 1. And it's not clearly. And then you say entry V is equal to time. And post visit is similar. So we'll just see what we are doing. Time plus equal to 1, exit to V is equal to time. Correct? So what does this do? Time is a global variable, and here I can even initialize time to be 0. time equal to 0. Correct? Now, so now what is happening? So we are time stamping the entry and exit of every vertex we visit. Correct? So let's run this on this undirected graph. Let me erase this edge, which is not there. So first, you will start from 1, correct? So you would pre-visit 1 and you would increment the time to be 1 and set the entry of V to be 1. So I will write the entry of V first and later on write the exit of V, correct? So this is 1 is the entry, 2's entry point is 2, 4's entry point is 3, this is 4, then you go below, so you get 5 and 6 and then 7, and I should have written with a different color. So let me just back. So let me write it with a different color. Which color should I write it? Like this. So 1, 2, 3, 4, 5, 6, 7, 8. Now I have to backtrack. So I will exit this, correct? Which means I will write 9 here, then 10 here, then 11 here, then 12 here, then 13 here. Now I go back here, but then I go here. So 14, then I backtrack from here 15, and then there is 16, and then there is 17, and then there is 18. Correct? So we get this tree with these entry and exit labels. So we have 1 at the top. So you have 1, and that has labels 1, 18. Then you have 2. This has 2, 17. Then this has 4. Let me try. 4. This has 3, 16. Then you have 3, which has 4, 13. And so on. So let's draw it quickly. 5 is what? 5, 12. And then 7 is 6, 11. And then 8 is 7, 10. 9 is, oh sorry, 6 is 8, 9. Correct? And then I have to backtrack all the way up till 4. And here I get another thing called 9. And that is 14, 15. Now, is there anything that you can observe about these? If you think of these as intervals, then this is a large interval. This is a smaller one contained in this. This is a smaller one which is contained in this, and so on. Correct? So the intervals are always contained in each other. Notice that here both these intervals are contained in this. And the intervals do not. So the intervals for a parent, the interval for a parent contains the interval for children and all intervals of siblings are disjoint. So this is what is called, tell me.
No, I don't understand how we're going from 3 directly to 9. Like, why is that? Like, when we backtrack, we reach 3,
We reach 3.
and then after that, we go directly to 9. Is
No,
that
we go to 4.
so? Shouldn't 4? Oh, okay, right. Yeah.
Here. Na? We reach 3, then we go back to 4. And now we find that 4 has another neighbor which is unexplored.
No, so but you marked 4 with 16, correct?
Yes, because 4 was not yet done when, so 4 would be done when 9 is also done. When I backtrack from 9 back to 4.
So I don't understand the numbering, like in the sense we like the timestamps. Okay, so
Yes.
starting from 7, like 7, the timestamp is 11, then we go to 5, which is 12, and then go to 3, which is 13. And then after that, what do we like? How do we jump from?
So we go to 14, correct? 14 is not yet done. We have not post visited it. So 16 doesn't occur. Remember, we would post visit it only when all the neighbors of for each edge VW we are and such that mark W is equal to 0. We are done with this, correct? Only then we would post visit 14, correct? So post visit 4.
So 14 occurs at 4, is it? Like the 14?
14 doesn't occur.
No,
14
like
tell me.
no, sorry, like the 14 stamp. Is
Huh?
that in position 4 or in the 9th vertex?
In the 9th. In the 9th.
Okay, so I'll think about it.
Because no, let me try to clarify. So you would you are at 13, you are at 3 with the thing 13, correct?
Yeah.
The pose is at 3 with 13, correct?
Yeah.
Now you go to 4. Are you done with 4? Not yet. You cannot post visit it, correct?
Right.
So you go to its remaining neighbor, and there you pre-visit it with 13 plus 1, 14.
Right.
And then you post visit it with 14 plus 1, 15. Then you come to 4.
Yeah, now I understand.
Okay. So you get a so-called laminar family of intervals. By laminar family, I mean that each interval is either completely disjoint from another interval or contained in another. Here 2, 17 is contained in 1, 18. 3, 16 is contained in 2, 17, and so on. 14, 15 and 4, 13 are contained in 3, 16, but are disjoint. Do you see my point? So if you draw these intervals, you would have a large interval for 1, from 1 till 18. And then you would draw this 2, 17. And then you would draw 3, 16. So this implicitly defines a tree, correct? 4, 13. So let me draw it. It is not to scale, but nevertheless, we draw 4, 13 and 14, 15. Correct? And then 5, 12, 6, 11, 7, 10, 8, 9. Correct? So this is another representation of this tree, and so these are nested intervals. That's what I want to say. And so is the idea clear? What is happening here?
Yes, sir.
Okay, good. Now, this we saw, remember we said that this was in undirected graphs. In directed graphs, what would happen? If you ran this procedure, so if you ran this procedure on directed graphs, what would happen? So let's take an example. If you have something like this is a directed graph, and let's say some directed graph, correct? Now, what would happen? Let me give numbers to these. 1, 2, 3, 4, 5, correct? Let me copy and paste the DFS Explorer here for your convenience. So tell me, what would happen? So I would first start with, let me put the labels again in. So I would start with 1, comma something, 1. I've not yet completed it, so I come to 2, and I put 2, comma something. I start this. Then suppose I go to 3, correct? So I put 3. But now notice 3, there are no outgoing edges. There are incoming edges, and in the undirected case, we could have gone to 5, but now we cannot because it's not an outgoing edge. Correct? So I would have to close this at this point and come back here. Correct? And now I go to from 2 to 4. So this is 4. So this is again 5, comma something. And then I go to 6, comma something. And now I cannot go forward. So I will backtrack. 7, 8, 9, and 10. This is fine because there are 5 nodes. Each node is counted twice. So we have done 10. Now, now what is the thing? Now are there cross edges? First, tell me that. Anyone? So let me mark the
3, 4.
So 3, 4. 3 to 4, there is no edge.
3 to 5. I mean 5 to 3.
5 to 3 is an edge. Yes. So this edge is a cross edge, but it is a reverse cross edge. Meaning, if you draw the tree, what will it look like? It will look like you have 1 at the top, then you have 2, then you have 3, and now you backtrack. And then you go to 4, then you go to 5. And there is this edge, which is, so let me draw it in a different color. There is this edge, which is a back cross edge, reverse cross edge. It's going from a larger interval to a smaller interval. Both the what do I mean by larger interval? Let me mark the intervals here. 1, 10, 2, 9. 3 is 3, 4. 4 is 5,8, and 5 is 6,7. So 3, 4 is strictly less than 6,7. Both the things are less than 6,7. And indeed, it is not. So you still get a laminar family. You still get nested nested intervals, but there are some cross edges also. But the cross edges are always from larger things with larger entry and exit number to smaller entry and exit numbers. Correct? Are you with me?
Yes, sir.
Okay. So an edge from a forward cross edge, this is not permitted. This is not permitted. Because if it were there, you would first explore it before, correct? Like we said, I should have drawn it with a different color. This is not permitted. If it were there, I would have discovered 5 from 3, and then this would not have been an edge, a non-tree edge, correct? Okay. That said, let's move on to something slightly different, which is related to this. Tell me.
So
Question.
could you just explain the last bit about why the forward direction is not permitted once?
Okay. So suppose this edge 3 to 5 had been there, a non-tree edge.
Yeah.
Okay. Then I claim this would not have been the tree. The tree would have been 1, 2, 3, and then 5 below 3. 5 would have been explored directly from 3. You would not have backtracked from 3 before reaching 5. So 5 would have fallen under 3's, 5 would have become 3's child, and then this would have become a reverse cross edge.
Okay.
Correct?
So why would I don't think I understand. Why would the second one become a reverse process?
Because let's do this quickly. So you would start with 1. Go to, suppose this edge is there, the 3 to 5 edge, correct?
Yeah.
So 1 which starts at 1, 2 which starts at 2, then we go to 3 which starts at 3, and then we go to 5, correct? Which starts as 4. Now from 5 we cannot go to 4, so this closes at 5. Then now 3 closes at 6, and 2 still has neighbors which as a neighbor which is 4. So this is what is the number? 7, correct? And now 5 is already explored, and now you can see that this non-tree edge from this 4 to 5 edge would be a non-tree edge.
Oh yes.
Because we cannot.
Yeah.
And now it's a reverse edge, and now we can just complete it. 7, 8, 2, 9, 1, 10. Correct?
Yes, sir. Thank you.
Okay. So that said, any more questions about this? If not, let me move on to something slightly different, only slightly. So we are going to talk about directed acyclic graphs. So for undirected graphs, acyclic graphs are very simple. What are undirected cyclic graphs? Acyclic graphs?
Trees or
Forests.
forests.
Yes, correct. So undirected acyclic graphs are equivalent to forests, and they have a very simple structure. But in directed graphs, because you can have undirected cycles or cycles, so this is a directed acyclic graph because it has no directed cycles, correct? So the structure of directed acyclic graphs is somewhat more complicated, much more complicated than undirected acyclic graphs, correct? So you can have something, and you can have this and so on, correct? So what is the use of directed acyclic graphs? What are the uses? Of course, it's a natural class of graphs, but in many places, it is of many natural situations can be modeled by directed acyclic graphs. For example, you can think of course allotment. Course, what is it called? Courses and prerequisites. So you have a set of courses, C1, this has some prerequisites, CI1, CI2, C1, I1, 1, I2, and so on, correct? Or let's just call it, and then you have C2 that has some prerequisites, C2, I1, C2, I2, and so on, correct? So basically you have a course, in CMI, you have a number of courses. Each course comes with some prerequisites, correct? The initial courses, the first year courses do not have any prerequisites. Later on courses have prerequisites which are ones in previous semesters. So this is a natural example of a directed acyclic graph, correct? All the edges point from so you can think of you can direct the edges from this to this. So from a course to its prerequisites. This defines a graph. What is the use of this graph? You can use it to find, let's say, the minimum number of semesters in which you can complete your degree. Assuming that you can take arbitrarily many courses in one semester, you can use it to find. So how would you use it to find how many semesters you have to do you see the problem? At least intuitively, do you see the problem? See the question rather.
So I guess loosely speaking, we could do what we did last time to mark the depth of everything, then count everything at each depth, and then
yeah,
basically
that,
like
yes.
allot credits in. Yeah.
So we'll come to the algorithmic aspect later, but what is the how does it model the natural thing is the question I'm asking. So my question is, if you have this course prerequisite relation given to you, how will you find out, at least intuitively, how many semesters you need to take to complete all the courses? I claim it is the length of the longest path in this graph. So length of longest path in the course prerequisite DAG yields the minimum number of semesters or whatever unit in which you do one course required to complete all the courses. So why is this so? So firstly, things without so how are we doing this? So suppose you have C1 that has some courses, some prerequisites, C2 that has adjacency list of prerequisites, the out adjacency list, and so on. And you want to compute when can you first take a course? So you can take a course when all its prerequisites have been completed. So firstly, there must, so let's draw an example. So you have some courses which do not have prerequisites. Then there are courses which have these as prerequisites, and there are further courses which have these as prerequisites. They can also have these or these as prerequisites, and so on. Correct? So the last semester's course, the last courses are things which do not have any courses for which they are prerequisites. Correct? So think of this as sink vertices, and these are source vertices. Usually it's in the reverse, but it does not matter, depending on how you put the arrows. You do it from courses to prerequisites or from prerequisites to courses, up to you. Let's do it from courses to prerequisites, correct? So now, intuitively, you can see that the longest path in this graph from a source to a sink will give you the minimum number of semesters required to complete all the courses. Do people see this? Is it transparent, or do I need to explain it? If there's anybody who doesn't see this immediately, tell me.
Sir, could you repeat the claim once again?
The claim is you look at all the longest, you look at all the paths in this graph. Correct? There are lots of paths, but look at all the paths. Take the longest path in this graph. Okay.
Okay.
So the number of vertices in that path is the minimum number of courses you need to is the time you need to spend to complete all the courses.
Sir, in that case, I think I'm misunderstanding something. It looks like we only need 3 semesters to complete everything here, but the longest path is 4.
No, you need 1, you would do this, then 2, you would do this, third semester, you would do this, fourth semester, you would do this.
So, but there's a course next to the one marked 3, right? Which looks like it doesn't need any prerequisites.
Yes.
So we could
this
say
can
that
be
we
done
do
at the first semester.
both.
Also.
Sorry. Yeah, no, I forgot we needed the other one also.
Yeah.
No, got it, sir. Yeah, thank you.
So you can do this in second. You can do this in second. I have not put any restrictions on how many courses you can do per semester. And instead of doing it in the second semester, you can do it in the third semester also, and so on. Correct? But 4 semesters is the okay.
But how to, like, when the number of courses can be taken in a semester is constant, how to solve that? As in, we can credit only 24.
Yeah, so that's a different question. Let's not go there for the time being. Correct? So So we will come back to that. So, but yeah. So now. So now how do you find, so basically you want to find a schedule for the courses, correct? You want to say that which semester, or which is the earliest semester in which a course can be done. How would you find that?
So I guess we could use BFS, what we did last time.
You could use BFS.
Because last time we were able to mark distances from.
No. We are, there we were doing shortest path.
So could you repeat the question?
The question is, we want to find the minimum number of semesters required to complete all the courses.
Oh, okay.
BFS would give you the shortest path, while we want the longest path in the graph, which is in general graphs a very hard problem, but for DAGs it is easy. So let me try to. The shortest path from this node to this node is just 2 courses, correct? You can go from here to here, and then from here to here. Time to courses, correct? I mean, so maybe I should, in the next class, I will reverse the pointers, which makes this more transparent. Or let's do this in reverse. So let me put the reverse pointers from a prerequisite to a course, correct? So I will reverse these pointers. That makes it easier to tease. And so what is the shortest path from this vertex to this vertex? Tell me. Consists of how many nodes? 1, 2, and 3. So the shortest path across a source and a sink is just 2 or 3 nodes, whichever way it is. The shortest path is not what we are looking for. We are looking for longest path. So longest path in DAGs.
Sir? Could we just keep like removing the shortest paths and like eventually we'll get.
That's a very good point. That's a very good point. Not the shortest paths, but let's see. So all the courses which have no prerequisites can be done in the first semester. Correct? These courses. Do you agree?
Yeah.
So you have 1, 1. And then you remove this. And now you have a bunch of. And now you can do this in the second semester, this in the second semester. Now you remove these. And now you can do this in the third semester, and this in the fourth semester. Correct? So intuitively, what we are saying is so let's call this topological sort or topo sort of G is equal to so maybe I shouldn't write it. Let's do it. Def topo sort G is G with a counter C is number. So I'm mixing things, so I should not. So longest paths in DAX, that's one thing, correct? But if you want to, so let's look at a slightly different but related problem. You want to topologically sort the graph. What do I mean by that? That is, give so you are given a graph G on n vertices, or directed acyclic graph G on n vertices. You want to give a number, a unique number from 1 dot n to every vertex, correct? Such that if u is so you want to give a number, let's say number d of v from 1 through n to every vertex v, says that if u is a prereq of v, then du is less than d of v, correct? So you want to number the courses so that a course that occurs, a course which is a prerequisite of another course, has a smaller number than the other course. Is the problem clear?
Yes, sir.
Okay. So how would you topologically sort a graph? And like someone suggested, the simplest way is find a source, meaning a vertex with no prerequisites or predecessors, give it so let's say while all vertices are not numbered, give it the next number and delete it from the graph, correct? So I've not yet told you how to implement this algorithm formally, but at least a naive implementation you can think of. You take this graph G, which is a directed acyclic graph, promised to be a directed acyclic graph. You find a source in the graph, and we will say why this source exists in a minute. But suppose the source exists, you give it the next number, and then you delete it and all the edges incident on it from the graph, and then you recurse. Correct? That is, you go back, you find a source in this graph, give it the next number, and delete it from the graph, and continue this way. So is the procedure clear?
Yes, sir.
Now you might ask me, why does there always exist a source in the graph? Why does a DAG always have a source vertex? That is a vertex.
Because it's a cycle.
That's true. But why? Suppose not. So suppose there is no source vertex in the graph, we should show some contradiction, correct? And this is often done by the longest path argument, correct? So consider the longest directed path P in the graph, correct? So what is this? What does this path look like? It looks like something like this. It's a directed path. It's very simple. Now I claim the first vertex in this path. So suppose this path is U1, U2, UK. Then claim U1 is a source in G. Why is that so? Because if it's not a source, it has a predecessor. Correct? If U1 is not a source, it must have a predecessor, say U0. Correct? Now, case 1. U0 does not belong to P. In case 2, U0 belongs to P. Correct? These are the only two cases. These are exhaustive cases. Now, I claim that neither of these cases can occur. Because if U0 did not belong to P, U0 is a vertex which is not on P and it has an edge to U1. This contradicts that P was longest path graph. Correct? Because you can extend P by adding this U0 U1 edge. U0 U1 to UK is a longer path. And if U0 belongs to P, if U0 is here and you have this is in case 2, then what is the contradiction? Tell me. Anyone?
So U1 is not the source, right?
No, we want to prove that U1 is not a source. What is the contradiction in this case?
It will be cycle.
We would get a cycle.
You would get a cycle. Very good. So you would then U0, U1, dot 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 till U0 is a cycle, which contradicts the acyclicity. So therefore, U1 is a source in the graph always. Correct? Another way to see this is very simple. You just take a vertex which has predecessors, look at one of its predecessors. If it doesn't have a predecessor, you are done. Otherwise, look at another of its predecessors and so on. In finite time, you must reach a vertex which does not have predecessors, because vertices cannot be repeated, because that would cause a cycle. So it's a rephrasing of the same argument in another way. Do you agree? Do people agree with me?
Yes.
So at least, so we can find a source in the graph with no predecessors and give it to the, so then give it the next number and delete it from the graph. Now you are left with a diagram. And now we just have to prove that this algorithm is correct. That is, what do we want to prove? That you will never do if there is if U to V is a path, you would have to do U in order to do the course V. Then du must be less than dv. This true, of course, for u comma v in E, and it's also true for these. Just the transitive closure of that. And I will let you think about it. So tell me, is this clear?
Yes.
Okay. So, okay. So I have done an intuitive way of doing this algorithm. We will look at it in more detail next time. Correct? Any questions? Comments? Okay. So then we meet next week. There'll be a quiz on one of the two lectures next week. I'm not sure yet which one, but one of the two we will definitely have a quiz. Correct? Okay, thanks.
Sir,
Bye.
the quiz will contain topics covered today.
Yes.
Okay,
Yes.
sir. Thank you, sir.
Okay, thank you. Bye.
Thank you, sir.
Thanks.